After 3 years of being in the PhD program, I am starting to transition into the research phase as opposed to the class taking, homework taking, test taking phase. And I'm still taking classes at the moment. I'm taking the class in Fourier analysis and convexity. And it's an interesting class, and I don't mind taking classes and doing all that stuff and reading these textbooks and learning more and expanding my math knowledge, but at some point you do want to focus more on research instead of just doing homework problems, because these homework problems I'm doing are very difficult. They take a lot of time, and it's not like we're kids anymore. We're adults. We have other responsibilities to take care of outside the classroom. So yes, you do like 5 homework problems a semester. That sounds like an amazing deal, but it's actually not as amazing as it seems. But if all goes as planned, I will do my candidacy exam this year. And what that means is that after you pass candidacy, you don't have to take classes anymore, and then you can just fully focus on research. And that's kind of what I wanted to talk about a little bit here, is what is the topic of my dissertation. So I am in the realm of convex geometry, and we use harmonic analysis, also known as Fourier analysis, as a tool to answer some unsolved problems in convexity. The reason I'm in this field is because my advisor did all of his research in that area, and you pretty much just do what your advisor wants you to do, because they're more able to help you, or they can help you more if you just do what they do, as opposed to bringing forth to them something that you've done in the past and say, hey, I studied, for example, fractal geometry, maybe we can do something in there. And he goes, well, I'm not really experienced in that, and if you have something very specific in mind that we could do, then you can talk and see if he'll buy it. But most likely he won't, and then you just have to work on something that he wants you to work on. And my guy, he's, of all the instructors I've had, he's given me the most open problems. The other guys, not so much. But he's given me a lot of open problems to look at, because he understands that if he just gives you one problem, most likely you're not going to be able to solve it, because that's kind of the big thing you have to get over. Is like, they give you a problem, it's like, okay, solve this, and then you can come back and get your PhD. It's like, that's not really how it works, because you may not be able to make any progress on it. So it is kind of an art form to figure out how to tailor a problem specific to the PhD student so that they can finish in amount of time, so they don't run out of funding, and then get the PhD that they got when they entered the program. And that kind of depends upon your advisor, like what is considered good enough. Some people in my department, like, they say 3 papers and then you can get your PhD. I spoke to 2 former students of my advisor, and it sounds like both of them wrote 2 papers. One was like with them, and then another guy said that there was, for example, this one guy wrote a paper with the advisor and then independently was able to write another paper, and he showed it to him and he was like, oh, this is a great result. So those 2 together sealed the deal for him. That's how he got his PhD. And in some cases, if you have one paper but the paper is really, really, really good, then that by itself can be considered a PhD, and that's kind of what this first open problem I'm about to show you looks like. So apparently this problem is pretty difficult. He showed it to us in the convexity class that I took, and he said that if you can solve this, then for sure this is worth a PhD, because apparently the reason why this problem is so difficult is because you lose a very useful tool in harmonic analysis called a convolution. This idea of convolution apparently is useful for a similar problem to this, but this is a much more difficult version of a previously solved problem, which I did feature on the channel. I don't remember which video it is in, but it's on the channel. So what does the problem say? You are given a set K a subset in RD, so this is Euclidean space, that is origin symmetric and a convex body. So origin symmetric just means that the center is, the origin is contained in K, but also K is equal to negative K. So if there's a vector in K, then negative that vector is also in K, and vice versa. I probably said that weird, but because I struggle to say things correctly, I'll just write it on the page, because I don't want to film this video again. Now, convex body just means that the set is convex. So if you take any 2 points in the set and connect them with a line segment, then that line segment is completely contained within K. And the body part refers to the fact that K is compact and has non-empty interior. So a lot of assumptions on K already. And then we have this additional requirement. For any U that's in SD-1, and this notation just means the boundary of the Euclidean ball centered at the origin, unit ball centered at the origin. So it's all vectors U such that the Euclidean norm of U is equal to 1, put it that way. For any U that we have, the D-2 volume of the boundary of K intersected with U perp. So U perp is the orthogonal subspace to U. We have that this set has D-2 volume equal to some absolute constant, which means that no matter how you choose U, you always get this constant that's in the end. So what is the question? The question says, does it follow that K is the Euclidean ball? Because obviously a ball will have this property. You know, it might be beneficial to see what this question looks like with a picture. So I've drawn a picture here. So this egg shape that I've drawn is K. It's not the best drawing in the world, but it's good enough for the purpose of this video. It's origin symmetric in a convex body, so you pick any U that you want, some vector U, and you look at the orthogonal subspace, which I've denoted U perp. That's the plane that I've drawn. And I should probably put a little angle here to show that it's a right angle. And then the question is about, or not the question, but the assumption is about this cross-sectional perimeter. So the statement really says the perimeter of the cross-section is always some absolute constant independent of the vector U. Does it follow that K is the ball? So if K is a ball, then this cross-sectional perimeter corresponds to like a great circle around the globe, if you will. And that's always some constant. So this is kind of saying, okay, look at all convex bodies, origin symmetric, that have that property. Does it follow that, the body is a ball? And that's an unsolved problem, and my advisor worked on it a little bit with another guy in the math department, and they got some partial result. They never published the paper, and I've skimmed through it. It's kind of a mess because it's a hard problem. And because of that, I'm a little bit intimidated by it. But I might come back and see if I can play with it at least a little bit. So that's this problem. If you can solve it, you get a free PhD. How about that? That's my challenge to you. Get this PhD by solving this problem. And then let me have it so I can believe. And then we have the second problem. So this problem is the only problem in this list that I have made at least some sort of progress on, and I'm using the word progress very loosely, but I can describe it here. So you have two convex bodies, K and L. 0 is contained in K and L, or the intersection of the two. So they both contain the origin. Let U be an element of SD-1. U perp is the orthogonal subspace. So if you want to know how this setup here is defined, it's written down here. And you assume that for any unit vector, there exists an SO D-1 rotation within the orthogonal subspace, such that the rotation of the shadow of K on U perp is a subset of the shadow of L. And then the question is, does it follow that the volume of K is less than or equal to the volume of L? So I believe that this answer is false. It's not true. You can have K bigger than strictly bigger than L, but that's just a belief. I have to play with the quote-unquote counterexample that I may have found. I say may have found because it could be, my example could be complete bogus, in which case, but I told my advisor about it, we played with it, so he seems to be on the fence with it as well. It's like some days he's like, yeah, I think it might work, and then other days he goes, nah, I'm not really convinced yet, but we'll see. But to describe this in plain, simple English, let's say that K and L are two convex shapes in 3D space, and they both contain the origin. Easy enough. You take K and spin it around in some way, take L, spin it around in the exact same way, and then you look at the shadows that they create when you project it onto some sort of space. Like, so I'm not describing the problem exactly as it's written, but in an equivalent way I am. So you spin them around, you project them on the paper, and this requirement basically says, okay, no matter how you spun them, you can always turn the shadow of K, or, rotate it, so that it fits within the shadow of L, which means that obviously the shadow of K has to be less than or equal to the shadow of L in terms of, the two-dimensional volume here, which is just area. So the area of the shadow of K is less than or equal to the area of the shadow of L. And then the question says, okay, now what does that tell you about the volumes of K and L themselves? And so naturally you might say, okay, well, maybe the volume of K is less than or equal to L, if this is true. But there was a paper written by Daniel Klein, which I mentioned on the channel before, where you had a similar questions about translations, and it turned out that this did not follow from that. So this is like a follow-up question about rotations. So that's what makes me think that the answer to this question is false. And that's kind of the problem that I'm most interested in right now, and it might be the thing that I do my candidacy exam over. Okay, and so now I think maybe we'll wrap up with, maybe one or two more questions, but this is the next question. So I got this from a paper from the same guy, and I thought the question was pretty interesting. So let's go through it here. You have two convex bodies in Euclidean space. We're told that the volume of L is positive, so we don't want any, trivial cases where, the volume of L is 0. Let K be between 1 and D minus 1, and let U be a K-dimensional linear subspace. So if D is equal to 3, for example, then a one-dimensional linear subspace is just a line that passes through the origin, and a two-dimensional linear subspace is just a plane that passes through the origin. But if D is, bigger than that, then you can have higher dimensional subspaces. So use a K-dimensional linear subspace, and then you look at the orthogonal projections onto U. So again, we're playing the same game with shadows. So we can call this the shadow of K on U and the shadow of L on U. Assume that the shadow of L can cover the shadow of U. So this is again by either translations, reflections, or rotations. In this problem, it was just rotations, but now we're also throwing in translations. So if the shadow of L can always cover the shadow of U, no matter what U you have here, this group here, by the way, is called, I think it's a group, I may have misspoken, but I believe it's called the Grassmannian group. You have to check me on that. I'm not super familiar with the Grassman, but I like the name, though. Grassman seemed kind of funny. But no matter what U you pick, the shadow of L can always cover the shadow of U. So the question is what is the best upper bound for the volume of K divided by the volume of L? And notice that this is the D-dimensional volume. So it is the legitimate volume of K and L. And I believe in the paper that I got this problem from, this open problem, they found an upper bound already. It's just D, less than or equal to D, which means that the volume of K is less than or equal to D times the volume of L. And so the question is about what's the best possible upper bound, which means you want to make it as small as you can so that it's tight. I thought this problem was kind of interesting. We deal a lot with upper bounds and lower bounds in analysis, and we've done that a lot over the past 3 years in my homework and in class. So that's what attracted me to this. Is like, maybe I can do something. Maybe Koshi Schwartz can come in here somewhere, but I don't know. I just thought the problem was interesting. Okay, so let me put that off to the side. For this page, I'll probably skip it. I'll just let you pause the video and read what some of these open problems are. Oh wait, this is the universal convex body problem, which turned out to be pretty hard. So I've talked about it before on the channel, so you can read it if you want. These two problems, by the way, I picked up from the conference in Banff that I went to a couple months ago. So that's where these guys came from. I thought they were kind of interesting. R, by the way, I believe, I don't think I wrote it here, but R, I believe, represents the spherical Radon transform, if you want to look that up.